All right, good morning. So again, as usual, please note everything is recorded and the lecture will be available on YouTube and on Canvas. Mind what you say, everything's recorded. Okay, good. So today we will look at yet another property of the Fourier transform. This is called the modulation property. So modulation is an extremely important concept. So modulation Fourier transform of a modulated signal. So recall Fourier transform x of t is x of f is defined as the integral of x of t where x of t can in the general sense be a complex function of time, right? And x of f can also be a complex function. So in the most general sense, the Fourier transform maps a complex function in time into a complex function in a frequency. So modulation is the process of multiplying the time function with a time varying complex exponential waveform. So I can write the modulation property, right? The modulation of x of t as follows. So let me write it over here. The modulation is defined by complex something like e to the j omega t. So we know that this function, right, has two components. From the Euler theorem, we talked about this before. From the Euler theorem, we know that e to the j theta is equal to cos theta plus j times sin theta, where j is equal to root of -1. So setting theta equals omega t, where this is equal to 2 pi f, and this is time. We can write e to the j omega t is equal to e to the j 2 pi f t. Let's say this frequency is what? Frequency, which is equal to what? Cos 2 pi epsilon t plus j times sine by epsilon t. So it has a cosine component and a sine component. Both the cosine component and the sine component are of frequency f0, f0. The only difference is that one part, the real part, right? So this is the real part of the signal, of the waveform. So I can think of this as the real part. I'm going to call it the real part. And I'm going to call this part the imaginary part. The real part is the cosine component and the imaginary part is the sine component. But both components are the same frequency f0, that offset by 90 degrees. So if you take a cosine wave and a sine wave, put a j in front and add them up, you get this complex exponential wave. So by modulation, what we mean is we multiply our signal x of t, which is complex valued. So I have my x of t coming in, the signal x of t, complex valued in general. I have a multiplier, it's called a multiplier. You can always call it some other stuff, we can call it a mixer. So if you look at a radio frequency design book, this multiplication operation, the mathematical operation is multiplication, so it's called a multiplier, but in the jargon, people call it mixers because it mixes your complex exponential signal with the waveform. And from here, we send in our complex exponential waveform, e to the j 2 pi f0 t. I can call this omega 0. So it is actually e to the j. So if I take this, okay, I can recall, if I take the real part of this, e to the j omega 0 t, out pops the real part, which is cos t. If I take the imaginary part, right, e to the j t, out pops the sine. So in standard mathematical notations, capital E, small e, square bracket means extract the real part. Capital I, small m, square bracket means extract the imaginary part. So we get this compound signal coming out. This is now the modulated signal. We can write it as xt e to the j So the modulation property of the Fourier transform says that when you multiply your input signal x of t, right, and get the multiplied version where the input side on this multiplier is e to the j 2 pi f0 t, right, that effectively doesn't change the spectrum of the signal. The Fourier transform shape remains the same, right? Its phase remains the same, but the whole function in frequency gets translated by f0 into a different place in the spectrum. So geometrically, what it means is that if I look at the Fourier transform of x of t, right, I can write it as, okay, x of t as a Fourier transform x of f. I can visualize it. This. So this is my x of f. This is my frequency variable f. So let's say that the spectrum of x of t is like so. This 2 is faked.
I have a quick question.
Yeah.
What is REF IM?
It's a function to extract the real part of this complex function, and IM is the operation to extract the imaginary part of that complex function. Right. Because this has a real part is cos omega t, the imaginary part is sine.
So the multi-mixer, that's what it does. It extracts signal for it.
No, that's not what it does. It multiplies x of t by this. That's what the mixer does.
Oh.
Right? But this is just to show that the real part of this function is that, and this is the imaginary part of this complex function is that. That's all.
Oh.
So if I call the spectrum here x1 of f, what the operation does is it shifts the function by omega 0. So I can plot a new spectrum, right, having the same shape, same height, same everything, but now in a different place. This difference, let's say this is 0, this difference is omega. This is called a frequency translation. It can shift the frequency to omega 0, but the spectrum shape and the phase remains the same. So everything is the same here, so it is exactly the same. Right? So we can write this function as x frequency variable is replaced by a new variable f minus x. It's a change of variables, right? So if I take f1 is equal to f minus f0, it's still the same function, but there's a change of variable. Everything is shifted by f0. That's super important in communications and signal processing because all radios, including all of your iPhones and Wi-Fi devices, everything works on this principle. It's needed for every single thing. It's perhaps the most important operation. Yes.
Okay, if I understand your graph, on the graph you took of the mixer here, the one on the one that's going out, that's the that's the E, that one, that's for the E, right?
Yeah.
Okay, thank you.
Yeah. Yes.
The omega naught, that's like the horizontal shift. So is it x of t ej omega naught? Is that the shift part?
No, omega naught is the shift part. So this is omega naught is in the circular frequency. So actually it's f0. So I have to make up my mind whether I want to use f or but omega naught is equal to 2 pi f naught. So this would be in, if this was f, I would write this as f naught. F naught and omega naught are the same, just divide, just changed by 2 pi.
So the omega doesn't have to do anything with the phase shift in the xtej omega t.
I didn't follow it.
That part right there, xtej omega t, right? The last the output for the Bluetooth.
Xt times e to the
Yes.
power j omega naught t.
Yes.
Yes.
The omega naught does that have to do anything with the function transformation?
Yes. So this is the time domain, right?
Yeah.
And this is the frequency domain. So what we are saying is, if I take this one, right, and I find the Fourier transform of xt e j omega naught t, that is equal to x of f minus f naught. It changes everything by f naught. No other changes. Yes.
Okay, so if I understand this correctly, so fbx1 of f is equal to the what we were talking about earlier, the x of t time the small x of t times the exponential function, right?
So I have x of t going in.
Mhm.
I'm multiplying that with exponential j2 by f naught t. And the resultant is this x of t times e to the j2 by f naught t.
Okay.
So if I find the Fourier transform of this compound result, I can express that answer in terms of the original Fourier transform of x of t by simply changing the frequency variable f with f minus f. It's just a change of variable. So the effect of multiplying only shifts the frequency variable, no other changes.
Okay, thank you.
So to follow up on this question,
Yeah.
The original function is x of t, right? That's
In
what
time
we
domain.
put in time domain.
Yes.
And then this ej 2 pi frequency time goes into it. So that's what makes the graph shift.
Right. Not only does it goes into it, it's multiplying this by that. So the two of them are multiplying each other.
So the output x1 of f is that x f minus f naught. That's the
Exactly. So what we are saying is x1 of f, right, is the Fourier transform of this one, which is minus infinity to infinity x of t e to the j 2 pi f naught t times e to the minus j 2 pi f t dt. So when I do that, I can directly find the answer as x f minus f.
I'm pretty sure there's no like, or you can derive it, but it takes a long time to get to that.
No, it doesn't get a long time. I'm going to derive it right now in 2
Oh.
seconds. It's pretty easy, but it's a theorem.
Okay.
So I'm just explaining what it does, but in the next slide or next 2 minutes, we'll derive it. So let's derive this. So the proof is pretty easy. Let's do it. So we have the Fourier transform of xt e to the j omega naught t is equal to xt e to the j 2 pi f naught t, right? Which is what? Let's say x1 of f is by definition the integral minus infinity to infinity in time domain, full time, real value time axis. The function of interest is this xt e to the j 2 pi f naught t. From the Fourier transform, we get the additional part e to the j minus 2 pi f t. So here, take a moment to note that this is my time variable. Dependent variable. Okay. This is my frequency variable. And this is a constant. Because that's coming from the complex exponential waveform that's modulating the input. Right? It's frequency, but it's a constant. This is frequency, it's a variable. We have a variable part and a constant part. So I can look at this exponential thing and I see that there are 2 terms of exponentials getting multiplied by each other. We know that e to the x times e to the y is equal to e to the power x plus y. So we use this simple theorem to rewrite this, just algebra. I'm having x of t here. I'm taking these 2 exponential parts into a single term. I can see j is common, 2 pi is common, t is common. So I can write 2 pi, right? Something t. I want to preserve the Fourier transform shape, so I put a negative in front, which means that I just put directly f here. I have positive f here, so this is negative, so I need a negative f here. Okay. Just algebra. So now I can write f minus f0. It's a new frequency variable, f1. So I get minus infinity xt e to the minus j 2 pi f1 t dt, which is directly by definition x of f1. Where f1 is equal to f minus f0. Easy piece. Everybody good? Yeah.
On that side, there's like a negative j 2 pi ft.
Yeah.
But inside of the bracket, it's just j. Where did that just j go to?
Where's just j? I don't know.
Like e to the power of j 2 pi f.
I am not following your question, sorry. So are you good with this answer, with this line?
There's a j and there's a negative j, but down there it was negative j. So what happened to the?
Oh no, so I brought in parentheses, right?
Oh.
So I simplified, I just took the common part out. Negative j, 2 pi and t are all common for both these things. The only things that are differing from this part to this part is f0 here, f3. So I took that inside the parenthesis and took the common parts out. I basically factored it. I took the common factors out. I took the common factors out, but I did it in one step. I took a negative out and I put t at the back just to make it look like a Fourier transform. All right, so now let's see how we can use this knowledge in the real world. So this is all imaginary. It has imaginary waveforms, right? But in real life, the imaginary part is imaginary by definition, that it doesn't exist. It's just a mathematical tool. In real life, you only have real things, real waveforms, right? There are no imaginary waveforms. That's why they call it imaginary, okay? So how do we map the math from this abstract mathematical domain of complex numbers into something that we can go to the lab and build, right? I'll show you how to do that. Super important, so follow closely. We are going to assume that our input signal is a voltage from some system. Let's say we have a radio, an antenna, right? And this is giving my x of t. So this is real value. This is a volt. So you want to change the frequency variable f by f0 by changing the frequency domain, but we don't have access to imaginary signals. We only have real valued signals. So the closest real valued signal that we have would be a cos wave. Let's say I'm going to multiply it by cos 2 pi f0, which is real value. Produce the modulated output or frequency translated output x of t cos . So now we change the mathematical model from complex x, complex waves e to the j omega t into real x and a real waveform that's modulated. Right? Both are real. Real times real is real out. Everything's real value. So this is something we can go to the lab and build, and in next week we'll show you how to actually do it. By we I mean you. You will do it. So how do we map this thing into the complex theorem that's coming from the textbook? So we can use the property. We know that e to the j theta, right, plus e to the negative j theta divided by 2 from trigonometry is equal to cos of . This is coming from trig. Basic high school algebra, right? If you take in high school, I'm sure you have trig, you know that you can express the cosine as the sum of two complex exponential components divided by 2. Yes.
So my high school wasn't actually as good. So I've never known to do that. Is there like any intuitive ways I can look at it to understand that?
Maybe there is, but I'm not aware of it. But for now, just take it as fact.
Okay.
But we'll talk about it. I'll send you something to look at. So you can think of it this way. So if you take the Euler's theorem, right? We know that e to the j theta is equal to cos of plus j of sine. This is for you, okay? So follow along. Do you agree with this?
Yeah.
So if I plug in negative theta here, right? I get e to the minus j theta is equal to cos of negative theta minus j times sine theta. Right? But cos of negative theta is nothing more than theta, so I can remove this. So I have like so. So if I take this as the first equation, this as the second equation, and say 3 is the sum of 1 and 2, I get e to the j theta plus e to the negative j theta is equal to 2 times cos theta, and this plus and minus cancels off. The sine part cancels off, right? So I can bring this 2 to the bottom, and voila. I think that's about the simplest you could do. Is there any other simpler way to say it? No. But that's pretty simple. It doesn't have to be more simple.
Thank you.
So it's good that we did that, because that's exactly what we're going to do. We are going to use this theorem to show that cos theta is actually this, right? So I can plug in the phase of this component as 2 pi f naught. So if I have e to the 2 pi f naught t plus e to the minus j 2 pi f naught t by 2, that is equal to cos 2 pi f naught t. I just replace theta with this. So now I can immediately plug in to this one, and I can write x of t is times, I'm plugging in place of cos this whole thing, right? I'm going to get e to the j 2 pi f naught t plus e to the minus j 2 pi f naught t by half. I took the cos part here, right? I took the cos part and I chucked that and I plugged in this part in place of it, because that's it. Right? Now we are in good shape, because now I replace this real valued cosine thing with two complex valued functions which we know how to handle from the previous theorem, right? We know how to model xt times e to the j 2 pi f naught t. We just proved it 10 minutes ago, right? So this is actually 2 of that. I have 1/2 x of t e to the plus j 2 pi naught t plus 1/2 e to the minus j 2 pi f naught t. So from properties of the Fourier transform, I can write the spectrum x1 of f is the spectrum of this part plus the spectrum of that part. The spectrum of this part is directly from the theorem. There's extra half in front, so that basically scales it. X f minus f naught plus half. Here f naught is replaced by negative f naught. That means all the frequency f naught values become negative of each other. X f plus. So you get two components. In the cosine wave, there's a positive component and a negative component in complex frequency. So the positive component results in a negative frequency variable shift, and the negative component results in a positive frequency component shift, and you have the two spectra adding up linearly. The scaling factor of half, that half is coming from these two.
Is that F? It's F.
Which one?
The second one.
This line?
Yeah, the last one. Yeah.
Yes.
Is that,
F0, F0.
is that plus or T?
This is plus. All right, so let's do something interesting. Let's do it for sine, right? So we did the version for cos 2 pi f naught t, right? So I want you to do the same thing, but you replace cos with sine.
So that little input with the triangle on top, that's the antenna.
It doesn't have to be an antenna, but I just chose antenna as a source, but it can be anything.
F minus F0 for the function of x and t.
So we got it because we proved it, right? So we said that if x of t has a spectrum x of f, right? If I have x of t times e to the plus j2 pi f0 t, the corresponding spectrum is f minus. So it's always the opposite sign. If you have a positive here, normally you don't write the positive, but we know it's positive. If you have a positive sign, the frequency change is negative. But if I replace f with minus f, I get a negative sign coming out. And when I replace minus with minus another minus here, the two minus cancels off and gets positive. So if I have x of t e to the negative j2 by f naught t, that's corresponding to f plus f naught. Right. So we have both these guys in the expression. That's why we get two components. No worries. All right, so let's do for sine. This you will do yourself. So now the problem is exactly the same. The only difference is that without a cosine wave, you're having a sinusoidal wave. So I can write the expansion for sinusoidal wave is sine of 2 pi f0 t, which is equal to, the expression is e to the j 2 pi f0 t negative e to the negative j pi f0 t divided by 2. Is that right? I'm writing in memory, so sometimes I can make a mistake. So you guys have to be on the dot and tell me, okay? So this is the corresponding expression for sine. So you can prove it in a similar manner. Write down the expressions and show that this is actually the case. Okay. So now you have the similar situation. You have two exponential parts, the plus and minus frequencies. The only difference is instead of plus, you have a negative sign here. So it's subtracting. So the two frequency spectra are subtracting from each other, not adding. And the scale factor, earlier it was just half, now it's half over j. There's an extra j. But that's fine because capital X of f is anyway complex value, no matter what you do. So you can scale it by any constant, including a complex constant. Remember, 1 over 2j is a complex constant. It's complex valued, or actually it's imaginary value, but it's a constant. So when you change the spectrum by a constant, the constant pops out of the integral and it just scales the spectrum by a complex number. Okay, so you do it yourself while I run to the airport for my meeting with Northeastern. I'm going to stop here.